Chapter 9 was focused on the idea of work, but Chapter 10 instead focuses on potential energy. Now, I am a big believer in potential energy. I think it makes more sense than work, and it's easier to keep track of than work. So my personal preference is to worry less about work because in most situations you can use potential energy instead. The idea here is not depending on how we define our system, we can either think about a force that is external to our system, doing work, or we expand our system to now have that force be inside of our system such that it is now an interaction. That interaction is within our system and can be considered now a form of potential energy for certain types of interactions. So what's important to realize here is that you can approach the same problem in different ways depending on how you define the system. So that's where it's important to do that explicitly and to be careful about how you do it. You can do the problem frequently in two different ways that look very different but get you to the same answer, simply because in one case you've considered an external source of work, and in the other case you've considered potential energy. So you need to be self-consistent in this, and my personal preference again is to use potential energy anytime that it is possible. So we're going to start here with a little bit of conservation of energy, and I call this part 1 because we're going to be adding different types of potential energy. So by the end of chapter 10, our equation is going to look a little more complicated because we'll have more types of energy to worry about. But I want to show you very clearly at the starting point. Now in this situation, and again this is kind of a special simplified case, we have an isolated system. That means there's no external forces acting on our system. All interactions are only within our system. So we think about the change in the energy of the system, it must be zero because there's nothing interacting with the system. We then look at the energy within our system, and we have kinetic energy and we have potential energy. The reason I'm explicitly writing a total here is the idea that our system might include multiple objects. So our kinetic energy might be the motion of different particles. Every object can have its own change in kinetic energy, and for instance this could be one block and another block that are both part of our system, and for each of these blocks you would calculate its kinetic energy by taking 1/2 times the mass of that object times the speed of that object squared. So later on we're going to just write this as delta K, but keep in mind that that does mean the kinetic energy or change in kinetic energy for your total system. So you must consider every single object. Similarly, when we have potential energy like this could actually be potential energy of multiple ways that are we can store energy within the system. So we are going to have more than one type of potential energy. The book makes it clear that the potential energy is really stored in the interaction of our system, not in an individual object. I'm going to admit that this is a case where I'm frequently very sloppy in how I talk about it. And so, for instance, when we talk about gravitational potential energy, it's actually true to say the gravitational potential energy stored in the interaction, for instance, between the ball and the earth, but we might be a little sloppy and say the potential energy of the ball. But that's not entirely the right way to think about it. So as long as our system is isolated, the change in our system energy will be zero, which means that the sum of the changes of the individual energies on the inside are zero. They can be transformed one into the other, but the total sum must be the same. So where we're going to make this more complicated later is that we're going to be adding work, external work that cannot possibly be included in potential, and thermal energy that right now we don't have.